Hi everyone, today we'll be discussing operational amplifiers, so this lecture focuses on that issue. First, we will discuss um, the operational amplifier. We'll introduce it, then we'll look at the basic functions and useful devices that can be implemented, and then we present examples of operational amplifiers, which are inverting amplifier, non-inverting amplifier, summing amplifier, and difference amplifier. So an operational amplifier is usually called an op-amp. Nobody really uses the whole word operational amplifier. So basically it's a voltage controlled voltage source. So I know it's very easy for us to find independent voltage sources, right? We can refer to batteries, we can refer to power supplies, and those are independent voltage sources. However, if we're looking at dependent voltage sources, so the voltage controlled voltage sources, for example, which we have seen in circuits, an op-amp is a very good example. So it's a combination, in combination with other elements, it can basically perform many different mathematical operations. So as I mentioned before, before digital signal processing or digital operations came along, analog signal processing was the main method of carrying on mathematical operations. So you would have amplifiers that were used to perform addition and subtraction. So there are four different operations that we'll look into here, and that's addition, subtraction, magnification, that is inverting or non-inverting. We will not look at multiplication, differentiation, and integration, but those are all tasks that can actually be performed with an operational amplifier. So here we're looking at a general chip that will include an operational amplifier. So there are pins that are just not used, and that's why they're referred to as no connection. These are the terminals that power the operational amplifier. So let's have a look at this circuit first. An operational amplifier usually has 5 inputs. One is the inverting input, so that's the one that connects to the negative terminal. The non-inverting input, which is the one that connects to the positive terminal. Then there's an output. But there are 2 terminals that actually power the operational amplifier. So we'll look at this in more detail. So here, V plus and V minus are the ones that power the operational amplifier. This is the inverting input, which is the one that is connected to the negative, non-inverting input, which is connected to the positive. And basically, the balances, they're not really that important, but they're basically connected to the ground. So an operational amplifier is referred to as an active element. The reason it's called active is because it's really a dependent source, right? So it actually varies its output based on the input that is provided to the system. Now, this is the actual connection you would see. You would have your input come and be connected across these 2 terminals, the inverting or non-inverting. And then you would have an output that is given with respect to this node and the ground node. So this is the 2 output terminal, but the second output is given by the ground node. Now you do have to connect the plus and negative to an outside power supply. So in this case, this is the power supply that is supporting the positive side, and this is the power supply that is supporting the negative side. So when you are in the lab and you have those power supplies, you would put them in independent position, and then you would connect one to the positive side, and you would connect one to the negative side. And that basically supplies the positive and the negative voltage that is required by the operational amplifier. Now, in reality though, an operational amplifier can be represented as you can see over here, right? This is the actual circuit diagram that we would use. However, as we move on from this slide and the next one, we are going to only focus on ideal amplifiers. So in regular amplifiers, what we have is that the output voltage, the open loop output voltage, so basically when there is no connection between the output and the input terminals, we're referring to the amplifier as an open loop amplifier. So there's no feedback from the output to the input. It's referred to as an open loop amplifier. So when there is no connection from the output to the input, and we are looking at an open loop gain, the output of the amplifier is given by the difference in the voltage between the non-inverting terminal and the inverting terminal multiplied by the gain of the amplifier. So A is the gain of the amplifier. Now, generally speaking, these parameters can be categorized as so. So in a realistic amplifier, the open loop gain is quite large. It's between 10 to the power of 5 to 10 to the power of 8. So the open loop gain of an amplifier is very large. In an ideal amplifier, it's infinity. So if we had an ideal amplifier, the open loop gain of the amplifier would be infinity. The input resistance of an amplifier, what you would find in the currently available amplifiers in the market, is between 10 to the power of 5 to 10 to the power of 13. But in reality, when you're dealing with an ideal amplifier, it's actually infinity. Now, output resistance. This is the output resistance. The output resistance of an amplifier is, generally speaking, between 10 to 100 ohms. In reality, though, so that's the reality of it. But in an ideal case, again, we assume it's at 0. And generally speaking, the voltages that you connect to supply the amplifier with the necessary power is between 5 and 24 volts. So obviously, the ideal case would be almost the same, but that's irrelevant. So we almost never operate an amplifier without a feedback. So without connecting the output to the input, we never operate an amplifier. The idea of feedback is that you connect the output of the amplifier to its non-inverting terminal. You never have a feedback from the output to the non-inverting terminal, right? So the positive terminal is never connected to the output. It's always the feedback going to the the inverting terminal of the amplifier. And that is the way we'll always see them connected. And this feedback is used to control the output of the amplifier, and so allows us to make sure that we don't have an output that approaches infinity. Feedback to the inverting terminal is always called a negative feedback, and that's the one we're going to be dealing with throughout this course. So the reality, though, what happens with an amplifier is that the output of an amplifier has a range. It starts from a certain point, it's linear, until it hits the saturation points. The saturation points are the places where the amplifier basically cannot supply any voltage beyond that point. And that voltage is determined by the supply voltage. So basically, because of the conservation of energy, the amplifier cannot generate more power than is being provided. So if you're providing it with being negative 24 volts to 24 volts, and if you try to amplify a signal beyond these ranges, then basically the amplifier cannot do it. It will clip off, and you will just get a straight line. And so, obviously, when you hit these points, it's the saturation region. Now you are dealing with a nonlinear operation, and as engineers, as I've said many times, we don't like that. So we usually try to limit the output to be between these ranges. However, in this course, we're always dealing with ideal amplifiers. So the characteristics are that we'll have an infinite open loop gain. We have resistance between the two terminals that is infinite, and we will not have any output resistance. The infinite resistance means that when you connect an amplifier to, for example, any source or any other device, you basically do not see any impact on it. So from a Thevenin theorem point of view, it means that the load does not have any impact on the amplifier and is load independent. Now, why can we make such an assumption is because many of today's operational amplifiers come very close to operating in that range. And as we discussed before, they have a very large set of input resistances. They have very large gains. They have very small output resistances. And so for that reason, we do not worry about that. So we will solve some problems using these characteristics, but let's go to look at different forms of amplifier. So the first form of amplifier feedback that we'll look at is called the inverting amplifier. So what you have is you have an output voltage that is fed back to the inverting terminal. As we always said, we're looking at the feedback that is always to the inverting terminal with a feedback resistance RF, and there is an R1, which is an input resistance R1. And then this is basically the terminal that is connected. And we ground the non-inverting terminal. Now, if we write the nodal equation at this node, which we refer to as node 1, we can arrive at these set of equations. We know that the current coming through I1 must be equal to I2. The reason for that is because the resistance at the input of this terminal is infinity. The resistance at the input of this terminal is equal to infinity. And so no current is flowing through here. Since no current is flowing through here, this voltage and that voltage must be also the same, or you would have a current flowing through there. So we now know that V1 is equal to V2, and we know no current is flowing into the amplifier, so we know that I1 must be equal to I2. With that assumption, we can write that Vi minus V1 divided by R1 must be equal to V1 minus Vout divided by RF. Now, if we plug in that V1 is equal to 0 because V2 is equal to 0, and I said the reason for that is because there's no current flowing from terminal V1 to V2, so they must have the same voltage, or there would be a current flowing, right? For that reason, we say that there is no current flowing. The voltage potential difference is the same, and for that reason, they have the same voltage, so V1 must be equal to 0. If we plug in V1 equal to 0, we arrive at the expression that is below, and if we go and simplify it with respect to Vi, the input voltage, with respect to the output voltage, what we have is the output voltage is given by negative RF divided by R1 times Vi. So by selecting RF and R1 appropriately, we can actually amplify the input signal by the ratio of RF with respect to R1. And this is important, right? Because now we have an inverting amplifier. The reason we call it inverting is because of this negative sign that shows up there, right? So that's why it's called an inverting amplifier. Now, obviously, there's an equivalent circuit for this, and I will not go into great detail about it. We'll solve some problems, but we will always assume an ideal scenario from here on forward. Now, another important amplifier is the non-inverting amplifier. The basic configuration of the non-inverting amplifier is almost identical to the inverting amplifier. So if you look here, again, we have this feedback resistance. We have the input resistance. However, now the input voltage is actually connected to the non-inverting terminals. Now we have this setup. So if we again write the KCL, we know now that we can do so. So we can say that I1 is again equal to I2. So in this case, 0 minus V1 divided by R1 must be equal to V1 minus V0 divided by RF. We do that, we find a new expression with respect to the input voltage and the output. And if you plug in the values, and the fact that we have negative feedback in the terminal tells us that V1 must be equal to V input, which is what V2 is. So V1 is equal to V2 because of the negative feedback. And so for that, V input is equal to V1. Plug those values in, solve, and now what we have is V out is equal to Vn times 1 plus RF divided by R1. So we get rid of the negative value, and for that reason we call this a non-inverting amplifier. It is a bit different that we cannot support gains less than 1. The lowest gain we can ever support is a gain of 1. And so this is an example of a scenario where we have no gain. This circuit is obviously referred to as a buffer, but is also used as a configuration to try to separate two circuits from one another. So a non-inverting amplifier that has no input resistance and no feedback resistance, but still has a feedback line, is referred to, as I said, as a buffer, and is used as a unity gain amplifier to separate two circuits. We'll solve some more problems related to non-inverting amplifiers. And now let's look at the summing amplifier. The summing amplifier is almost identical to the inverting amplifier. It's just that we will have multiple terminals to connect the different input voltages. If you actually write down the circuits, what we have is an I1 plus I2 plus I3 is equal to I. Now, I1 is given by V1 minus VA divided by R1, VA being the voltage here. I2 is equal to V2 minus VA divided by R2, and I3 is equal to V3 minus VA divided by R3. However, VA is equal to VB, or the V non-inverting, which is equal to 0, so we can plug that in. But we also know that I to the output is given by VA minus V out divided by RF. You plug all of this in, you solve for it, and what you arrive at is this expression over here. Now you're summing the inputs to arrive at the output. There's a negative sign there, but that's not an important issue here, is that we have a negative sum factor, but still we are able to sum the amplifiers. We'll solve some circuits and problems related to that. Let's look at the difference amplifier. So the idea here is now, instead of being able to sum them, we're looking at a difference. And obviously you would think that, well, if we're trying to do that, we're going to take an advantage of a non-inverting amplifier and an inverting amplifier. So in this case, we'll connect the input that we want to be subtracted from one another. We put V2 at the non-inverting terminal, and we put V1 at the inverting terminal. Now, if you do so and apply KCL, what you will arrive at is that V out is given by R2 divided by R1 plus 1 times VA minus R2 divided by R1 times V1. Right? So that's easily determined. However, we also know that VB is given by R4 times V2 divided by R3 plus R4. The reason for that is because we have a voltage divider here, right? So there's a voltage divider that is placed there. So the VB is given by the voltage V2 divided by R3 plus R4 times R4. So now with the negative feedback present, we know that VA is equal to VB. We know that, so we can plug what it is for VB in this expression. Basically, we know VB is equal to VA, so we can put in VB instead of VA here. And we arrive at this kind of complex expression for V out with respect to V2 and V1. But we can see now with different ratios that these two are basically being subtracted from one another. We can select the ratios appropriately, so V2 is subtracted from V1. And if we make sure that R1 divided by R2 is equal to R3 divided by R4, we actually come up at a much simpler expression, which is V out is given by V2 minus V1 times R2 divided by R1. And that's exactly what we wanted to see. We wanted to see a subtraction. If we said R2 equal to R1, we get a very simple subtractor. So with this, we come to the end of the amplifier discussion. We'll discuss more related to amplifiers later, but we'll also solve some more questions in class. And thank you very much.